with the tradition now for the last couple of weeks of having another student speaker from the completing PhD program. And today's speaker is Denis Mulumba from the CMSE program, who's working with Liviero here. So, and Donna, sorry, yes. As we saw on the slide. So anyway, thanks, Denis. I'll turn the time over to you.
Thank you, Grady. Hi, everyone. Well, I'm already introduced. So I work with Professor Liviero and Rose, Material Lab, Chemistry Department. And on this project, we collaborate with Professor Donna, Math Department. As some motivation, I really wanted to give a brief intuition of why we want to do what we do in our lab, and maybe in different labs, I don't know. But if we think about the earth, everything in chemistry or science, that is physics, material science, engineering, we deal with systems, we deal with materials. We want to see how different materials interact with like different kind of environments and how they behave. For example, we want to ask questions like, how is ammonia sensitized to have agricultural fertilizers? How do we come up with the transistors? How do we come up with the diodes, stuff like that? So we kind of come to the conclusion that we have to deal with different materials, and then the choice of the material to pick depends on like what you want to achieve. And in several situations, the materials, even though we want them to be in isolated systems, they won't get to that kind of, we won't have them in isolated, we won't have them in a vacuum. So we are going to deal with problems, which is a mathematical problem here, one or two, we shall see. But asking ourselves that if we want to solve something that is exposed to wet environments, how do we deal with it? And now, as I've said, chemists, material science, and engineers can model that as a quantum mechanical problem. And we can always look at, if we go back here, we have this system here that has several atoms. An atom has electrons and stuff. We have the nuclei and stuff like that. And the question is, how do we have the system set up in a mathematical way or in a physics way? Physicists talk about the Schrodinger equation that models like how that system behaves. Kinetic energy, the interaction between the electrons and the nuclei. And then we have the interaction between the electrons themselves. The equation that arises here is really complicated, has no analytic solution. And the question arises on how do you have to deal with this problem that has no analytic solution. We do several approximations, different methods, quantum mechanical methods of solving this. And one of them is the density functional theory that we can use to solve such a problem with some assumptions. One of the assumptions that is based on the Poisson equation is this: like, instead of looking at the whole individual system, atoms in the system, let me say individual electrons in the system, each at a single time, we instead look at it as an electron density problem. So we do electronic calculations on such a problem. And the DFT perspective is we now can model that instead of looking at a complicated problem that has electrons, we have to solve each and every, this moves from any number that we have, then we have to modify and solve something like this. Plus some equation that I didn't include here, maybe I have it here. That is the extemporation that models something beyond what this doesn't talk about. Now, since we are solving an electronic problem, electronic structure, we want to look at the most stable structure or system. We want to, sorry. We want to look at, if we are solving a certain system, we want to look at it in the most stable state possible, maybe minimize its energy or thing like that. And the way we do it is in mathematics, or in a mathematical way. We want to think about the interaction between the charge density in the system and the electrostatic potential modeled in form of what is more common in math, that is the Poisson's equation. And the Poisson's equation might vary depending on which kind of situation that you're at. If you go back to the first slide, the motivational slide, and look at just the single system that we have on top, this one here, it is an isolated, in an isolated environment. We do not have anything like a fluid interacting with it. So that would be simple to solve. And that's in a vacuum, we have the normal Poisson's equation. The left-hand side, this is the electrostatic potential. And then this is the charge density, which is a function of space, depends on space. What we do in material lab is in 3 dimensions. And then that is not always the case in real life. We have wet environments almost everywhere. You might find that the molybdenum disulfide that I've shown in the motivation is interacting with water around it or any other liquid. So the problem that we want to solve now becomes a little bit complicated, and we call it the generalized Poisson's equation in this case. Or we can even have the Poisson-Boltzmann's equation if we have ionic situations, if we have ions in the system. Now, there's a little term that I've introduced here, and I want to call that the dielectric function. Several, I think, research has been ongoing, starting from the PCM models, the polarizable continuum models, and coming to the fatigator MTI. Then what we do is, like, how do you solve a system that is exposed to wet environments, but introducing what we call a continuum? So something like you have your system exposed to a wet environment, then you introduce a cavity around it. So that cavity is what, let me say, distinguishes between the wet environment, if this is water, plus the system that you have inside, which is a quantum mechanical system. And what has been done before to solve such a problem, this one here, maybe this as well, is the PCM models have actually used some out grid to just discretize, map the system from a finer grid to a coarser grid, then back to a coarser grid. I mean, to a finer grid. If you use the V, let me say V type, you start with a very fine grid, then try to restrict the solution you get to a coarser grid up to the smallest matrix you can think of, and then get back to the final grid by interpreting those results. But that comes with some costs, or maybe even computational time. Now, what Oliviero, who is seated just right there, and the friends have done is to design the self-consistent continuum solvation models. And that is basically translating this epsilon that we've seen So I have to go back. So that it depends on the charge density in the system. I don't want to go deep into this, but maybe I'll just leave it at that point. But the general problem is we want to solve something like this, and then the headache we have is this doesn't look like that anymore because of this term. You cannot just throw it the other side. You have to do either some math and make some assumptions, physical assumptions that make sense, and so that we still have our system and we can solve it really well. Now, if we think of this dielectric or the system that we have, if I can do something small here, like grid, and then we have our system inside here. And then it's exposed to some its environment outside. So what we have here is a solid. Then we have some solvents here. Let me call it just water for now. So we want to define the dielectric function because that is as a result of the introduction of the liquid that is outside of our quantum mechanical problem that we have inside. We want to define it that it's maximum outside and then the most minimum possible, let's say it's the one outside here. And then, so what the reveal does is to find a smooth transition, defining this epsilon, finding a smooth transition from the 8 to the 1 around this, the interface that we have. Now, a mathematician would just think about discretizing that, which is what we always do. And that epsilon r has different properties that I don't want to go to for now. But the question is, if we have epsilon r, and then our system is now complicated, how do we solve it? That is the question, because it looks now, it is back to us, the mathematicians. How do we solve the problem that we have? Well, we have attempted to solve it. One, if I can start with the Poisson-Boltzmann's problem, we can solve it. We think we can solve it. We are going to try that. Maybe we've tried it a little bit. Using this method that I want to start with, the direct inversion to relative subspace, which is just a form of Poisson-Newton. And all of that we are going to see is just optimization problems. So we just need to solve, if you're minimizing E, you just need to solve the problem that looks like. So it's R as well, plus some error. And the challenge is to minimize this as much as possible. So that is the direct inversion to relative subspace. And we minimize this. This is just the error difference between if you started with an initial guess of pk and then you have the next guess of pk plus 1. You want to see the difference. If you have the threshold that you need, the tolerance that you need, then you can conclude about the p. So this will solve our nonlinear problem that we've seen, the Poisson-Boltzmann's equation. We haven't tried that yet. But some people have done. Sure. Then this, I learned it in Brady's course, the Gimres. We won't solve our problem because I think the matrix that we have is clearly ill-conditioned and the system, the result won't be stable. We tried doing that and the result was not so nice. I want to go to the most important ones, the first two that Olivier tried solving and he has assisted me to solve. I hope I make him proud. But as well, I want to go deep into that. The idea is for the fixed point iteration, we start from a certain initial guess, and then we want to converge to a certain problem, to a certain solution that maybe is close to the analytical solution of the problem. It is a numerical problem. So we are getting a numerical answer. And then the choice of the initial guess is also going to determine what we actually learn to, and the amount of time that it takes solving. The problem that we are solving, if I can write it down here, is so what it is as the collaborators is to try to write this problem into a vacuum like Poisson's equation that we started with, something like this. And that was possible because he could distinguish between the charge density, I think, of the solute and the charge density that is as a result of the polarization charge that is in our system because of introducing the dielectric function, the weight environment. I don't want to go much into that. And then the second method that has also been tried, and the results are there, nice ones, is the preconditioned conjugate gradient. This is a modification of the steepest descent. We look into the steepest descent, but we look smarter. We do not want to move. We want to look in a direction that is a conjugate. And then that means the convergence will come actually much faster. And beyond the conjugate, started with steepest descent, conjugate gradient, then beyond this, we can think of a preconditioner and write the preconditional conjugate gradient. And the choice of the preconditioner is actually a big issue, because if you choose it wrongly, then you do not have a symmetric and positive definite matrix. That means you cannot attain convergence. Now, the idea of moving from the steepest descent maybe to conjugate gradient, or this problem, to this level, is you want to solve a system that has a matrix that has a beta conditional number. The conditional number is something that we use, I think, really will be disappointed if I don't explain this well. But the conditional number is something we use in numerical linear algebra to determine, we use it as part of the baseline to determine the stability of the matrix that we are solving. A smaller perturbation in X can just lead to a very big divergence in B because of the nature of A that we have. So that is the conditional number. That is the measure of how stable this A is. And the idea of this preconditioner is to move from, let me say, a matrix A that has a slightly weird conditional number to a beta matrix that we solve here, let me say M inverse A, that has a beta conditional number. And when we do that, well, the system that we are solving, the choice of the preconditioner that were used was epsilon n epsilon 1 minus n this n is 1/2. So that such a system will have a matrix will have a matrix that is symmetric and positive definite. The choice of n being 1/2 worked really well. We tried changing the n to something else and we didn't attain the convergence that we needed. Maybe the matrix that we attain is not symmetric and positive definite anymore. And that is why we had to think about a better way, maybe another way, not sure whether it is better yet, of solving this kind of problem. And that is why we collaborate with, we shall get there. But this is just talking about the convergence to show that the fixed point iteration is solving the system with the original A. If we improve it with the preconditioner, then we have convergence that is a little bit, I think we have it attained faster. That is just the convergence plot. Yeah, I'd skipped that slide in my mind. Now I can get back to what I was saying. After doing that, that is already done, and the paper is published. Now, the major task is to think about what else we can do to solve such a system, maybe have better convergence from the methods that we've seen before, or even a method that solves it as much as those ones that I've done. So that brings about what I wanted to talk about today, which is the masked interface method that we are currently working on. Now, I want to summarize this in some sort of geometry. I think this will summarize everything that I want to talk about. Now, if we are solving a system numerically, in most cases, let me say the 1D case, we shall talk about a 3-point tensor. If you're solving a problem at this point, U, I, J, then you want the solution here, maybe the point here. So this is translated by that. I think I will need this. It is a 1D starting. I'll just write that. And then, so we need this and that. If we try to think of, because the problem we are solving has an epsilon that is discontinuous, if we think of a 1D case, and then we have something like this as our function that we are solving that has a discontinuity somewhere. And then you're trying to discretize such a problem, I can even just let this come down here. Can be any function. So we're trying to discretize such a problem. If this is a grid point and a grid point at this point, and then you want to get the solution, the numerical solution for this specific guy right here, we need a solution here that we don't have. So we want to find ways of borrowing what we have down here and translate it down up here so that we have a 3-point tensor working out really well. So that is the general idea in a 1D case. So taking epsilon r, which is discontinuous, in this case on the right-hand side, makes the right-hand side of my problem discontinuous. And that means we have the same problem, but now in a 3D sense. And the question is, how do the steps that we use to do this? Now, what we're going to see forward is, if we write for 2D now, I want to get a 2D and say the 5-point tensor for 2D. And remind me this. Just checking. Which? The 5-point tensor for the 2D numerical. If I want to discretize. She's doing small transfers. Yes. I was just checking to see Anyway, yeah, Stanley, this should be.
Which is still very recent.
If I want to write a 5-point stencil,
Anybody who's taken five, anybody taken
Yeah,
565,
yeah, so
567?
you-
Are we, do we allow them to graduate?
yeah,
Yes, you,
Plus UIJ.
UIJ.
no, you're finished, IJ,
Mhm.
I minus one.
Okay.
Then plus U. J plus one,
Okay.
yeah, then they have.
So what is done is writing for the X first, then writing for the Y, right? Okay. So this will be right? Is equal to certain F. So that was the first one distance case. Disorganized my plots, which was discontinuous. Solution there. So for the 2D case, it's still the same problem, but in the 2 distance, all the 3D case will also be the same, maybe a complicated or weird shape that we have. But then we want to find something that adds here, maybe times H squared. So that we have, oh, this is over 1H squared. So that we have a corrected problem, so that we have something that we can discretize. Either if you do not do that, then you are not going to get the right numerical result at that point. So the procedure that we are going to go through is, one, how do we discretize? What do we do to get to this C that we had at this point, this correction at that point? And well, we are talking about discretizing, and the systems we've seen already are put somewhere. So I'm going to start with just a simple example of solving the Laplacian. The right-hand side is 0, and epsilon r is 0. And we are going to do something here that's, well, it is intended to aid learning. Maybe in the future, or even now, we shall change that. But what we are doing is, we want to solve a problem whose solution that we know. So I want to solve, I'll go away from the electrostatic potential phi and use Q. Supposing the solution is known. And let me say I'm solving it. So I'm assuming that the solution is different outside and inside. I'm going to define those regions and as, let me say, U plus and U minus to define the solution inside and outside respectively. Now we know that there's a unit sum around here and then the solutions are different. So how do we deal with such a case? That is what we are trying to answer.
I'm confused a little bit.
Yeah.
Where's epsilon and how does that fit into this?
Oh, okay.
What is discontinuous and where is the discontinuity show up in the problem?
Okay. Yeah.
Yeah.
Yeah. I said I want to use what I went through to understand what we do now to explain, maybe Poisson, maybe someone else can grasp. So what I did is, what we did is to assume that we now have a solution. First, move away from this problem that is actually squared. First, assume that this is 1. And then let's first take away this. And then we assume that we know it's
Oh,
the
okay.
solution.
You're not gonna solve the problem, you're gonna apply.
Yeah, yeah, yeah.
You're gonna apply the operator to the solution
Uh-huh.
and show me that there's a jump over this circle. I think. Okay, I'll be quiet.
No. Before I answer a question, maybe yes, yeah. Yeah, so I'm assuming that the region within, let me call it U plus, and then outside U minus. Yes.
Then what will from the boundary is-
Yeah, so this is just a unit step, and I'm assuming that maybe I don't know the solution outside, and that's why we have a discontinuity. That's why the solution is different. U is 0 and U is 1, outside and inside. So we are trying to correct the solution around this unit circle. Red, could you ask your question in a different way?
I guess I thought you were solving the equation, but I don't think you're solving.
Yeah, at this point, I'm not solving the equation because I'm assuming that I know the solution so that I can use that.
Mhm.
So this is the kind of steps that I went to before I went to like the next step was to understand what is going on. And what is the way I wanted to do that is, let's assume we have a solution.
Mhm.
And let's first take away, not what about epsilon r. At this point, the discussion is on what is epsilon r, how do we take it on the right-hand side? That is going to even take place after the presentation or discussion. But for now, we're assuming epsilon r is 1. We are diverging away from the actual problem that we want to solve. And so I just want to use this to explain it a bit of what is going on. Then we shall see what we're supposed to worry about the due process. Okay, so after the discretizing and just making sure something. Okay, yeah. After doing whatever we've done here, so this is just to show that we can have a solution outside and inside. I'm sorry I didn't label the U plus and U minus or 5 plus 5 minus on my graph. I hope you keep that in mind. So the whole point is, I've taken it off, is to get the C that I got there. So that we can, because we already know how to discretize the 5-point stencil, we know how to do that. Then the question is, now how do you design the C so that you have a better numerical solution? And that is what I want to go through. And so this is what Sandra and Stanley have given me. The first one, that is just the 2D discretization, 5-point stencil. And then I want to correct that for specific points, maybe around that interface, add some C. So the question here now is, in the abstract, I said, how do we design this C? And that's what we want to go through. Well, the numerical construction of C takes some steps. I want to figure out what I call the irregular points. For example, if I now draw something else here. So
You draw your interface so we can see it a little better.
So grid points, these are grid points. I want to mark some of this. That's good. So around, let me say if I'm standing at this point, for me to get the solution at this point, I need the solution here, this point, and that point. But well, this point is outside of this region. If I call this, let me say omega plus, omega minus, the solution at this point needs the solution here, but it lies in the omega minus region. So if I try to write the 5-point tensor at that point, then I have something like guess one. Yeah, let me use ui plus 1 at this point. Oh, where am I starting? Ui plus 1 j minus, this is a plus, this region is the plus region, that's the minus region. Let me just say plus this point, ui minus 1 j, this point, ui j minus 1, that point is minus 4 uij. All of these are pluses, but the solution here is the u minus. So that is I j plus 1. And that is a problem because these are different functions. So we don't know this. That's what we want to correct. And every point that has such a behavior, the point that straddles this interface, is what we are calling the irregular point. So that is what I'm trying to show here. Try to identify the irregular points in the problem so that we can correct at each and every irregular point on my grid. And then the other question would be like, how then do you do that? Well, we need to parameterize whatever interface we have. For now, I'm using a unit circle, but that won't be the case for our problem. It will be something beyond that, maybe complicated. Not maybe, it will be complicated, something like anything, any shape, because we shall not have an ordered system. So I parameterize this part, the curve. For example, if I'm parameterizing a circle, then I need to define everything in terms of the radius and the angle, right? So x cos theta, x is r cos theta, y is r sin theta, and then I pick up from there. So I parameterize everything, and then I need to know the closest distance from each and every interface, irregular point to a specific point on that circle, parameterized circle. And then after that, I can design or define what we call the jump conditions. This is the same reason as to why we've started with a solution that we know, so that we know how this works, then we can think about a bigger problem. Now, in the end, I want to use Taylor series expansion to correct each and every irregular point that we have. And we do that by defining jumps in the problem. Now you could think about the jump.
Sorry, the J here has nothing to do with the J on the grid, right?
Yeah.
Okay.
Okay, so let me say if u is x squared, that's u plus, u minus is 2x, I'm just assuming. And then the interface that we have, g of x is x squared minus 2x. I don't know if it will make sense, I want to use it to explain. Now the jump, that is the difference between u plus and u minus, is what I'm calling j of u, the j of phi in that case. And that is going to define, I think, the interface function in this case. Now, because we are dealing with a 2D problem, we want to get the jumps in the first derivative, the jumps in the second derivative, uxx, call it phi xx, or uxy. And these are the definitions that we have. Having those and knowing the distance of every interface point from the closest point, then we can define the Taylor series expansion that we want to use to correct our numerical solution. So this is just the Taylor series expansion, the 2D one. written using the jumps. And D is as defined, the distance from every closest point to the interface point. We do that for each and every point, that is the X coordinate and the Y coordinate, that for each and every regular point. But then if we can go back a little bit here, the problem that we want to correct, we can either subtract off or actually add on. So the question is, when do we add on? The sigma is just something that is either -1, +1, or 0. It is going to be 0 if our point is not a regular point, because we don't need to correct anything. But it's going to be something either 1 or -1, depending on where whatever I want to correct lies. If I can go back to this plot, the 1D plot. So if I can go back to this 1D plot that we had, with a point here, a point there, and then we need a point somewhere to correct this. We write a 1-point stencil. UI. Sorry. You're good at doing this. 1-point stencil. UI +1. Just like that.
You're going from, okay.
I'm just correcting 1-point stencil, just 1-point stencil. 3-point stencil, sorry.
Yeah, there is
Yeah.
one.
Sorry, this one.
Yeah, so UI plus UI equals UI minus UI minus 1.
This is
-2. One of them is -1.
so we want to add something there, and I want to call this plus sigma. It's equal to sum f, which is 0 for this case. So if this is a plus and this is a minus, I want to call this plus, but this is a minus. Well, this is, sorry, I'm going to use minus, plus, minus, plus, and a plus. So UI +1, if this is U plus, this is U minus. There's a difference. This is what we want to correct. And what we want to correct is going to be defined by this jump. Now, this part is going to be a negative. If I want to move something from the U minus to the U plus, or I'm going to add it there if I want to. Sorry, I can get to find the jump here. So the jump is going to be U plus minus U minus. That is the jump. And if I get this and add it at this point, some of this will have to cancel out. And what is going to cancel out is what I don't want, which is the minus UI. I'm just writing this as this because I'm in a 1D sense. But in a 2D sense, I'm going to expand the Taylor series, stuff like that, and have something of that sort. So if I get this and add it here, plus sum h 1 over h squared, which defines the correction term, then I have a correct 3-point stencil, because this is going to cancel out with that, and then I have something in the U plus sense, and that's what I want to do. So this sign is trying to assist us to move something that we don't want from the 5-point stencil in a 2D sense, and it introduces something that we want in the sense of U plus or U minus or phi plus, phi minus. And well, we've done everything on a unit circle, but what we deal with, if you looked at the system that we had in the motivation, is more complicated. It is an interface that is not a unit circle. First of all, it is in 3D. We've not gone there yet. We are trying to design everything in 2D for now. If it works, then we shall translate everything in 3D. But the most closest that we can have is something like this. Atoms lying inside here, and then the liquid, and then we have an interface epsilon. So whatever we've done with phi, Laplacian squared is 0, is just to help us to understand how this correction term actually works. And we have tested the correction term in its works for each and every kind of shape that we have in 2D for now. Some of the examples are those shapes that I generated here. And then we want to, after that, we shall now see how we do the jump stuff. But to actually ascertain that what we are doing is right, we had to do some, I don't know if we call it benchmarking, check if what you're doing is right in regard with what is there. So we have a smooth function already, and then we find a way in Python to have this smooth function created as with some discontinuities to see if we do not correct, we have a better solution, or if we correct this, problem with discontinuities, we have a better solution or not. I don't know if my English made sense there. But the idea is you have a function, then how does the truncation error look like? Do we have convergence or not? The formula we see is a little bit familiar to mathematicians, just getting the solution and then the numerical one. And when we do that, for any function, I think I didn't report the function here. I just wanted to show that our correction term works really well. We see for a smooth function, which is a green one, if we correct the solution, we actually have near the same kind of convergence. But if we do not correct, if we don't add the correction term, because then the 5-point tensor is, the rule is disobeyed, then we have something that goes off. The solutions, this is the one norm, this is the if norm, are different because the one norm takes the average of everything, the errors. The if norm will take the maximum. That's why it's kind of convergence a little bit. Well, that's to that. And well, now we weren't happy. We were happy that we have the correction term that works, but we have not solved the problem anywhere. Well, we started before I came to this presentation, but the idea was, how do you now get C? Because if you have C, our F is clearly defined well, and then we have our A clearly defined well, we can have a better solution. So now the challenges that arise here are, in the due process of getting C, we need jump conditions. And the jump conditions that we had were defined in terms of the solution that we knew then, but we don't know that. So the challenge that we have faced is, how do you get the jump conditions and use them, because we can get the regular points. Then use the jump conditions, get out the regular points to design our C. So that is kind of what we are doing right now. And so in a 2D sense, all that we know is this, but we don't know the solution. We don't know the solution. We know this because we can say the solution inside minus the solution outside is equal to this, the interface function. So this one we can get really well, but we don't know any of this. And the question is now, how you get those so that you can write your Taylor series expansion and use that to correct your solution. And then Donna in her book, I think it's a book, but published, very big. She used such kind of jump conditions to actually solve the Navier-Stokes equation, I think for some fluid flow. And I'm going to try that. And the idea is, since I know the interface written in terms of my parametric equation, then I'm going to translate everything into the parametric equation. Then the challenge is, this wouldn't be a challenge, I think. Well, for complicated problems, it will, but just designing the normal, something like that, function. Then I differentiate in terms of with respect to the normal, and then I'll have those. So at each and every grid point, we shall have to solve a 6x6 problem because there are 6 unknowns, 1, 2, 3, 4, 5, and 6. Then use this to get information about this. Then we can correct our result. So that's it.
Questions?
Yes.
In the next step, you started with just a simple homogeneous system where you knew the solution in and outside.
Yeah.
Just to kind of a sanity check for your correction error, right?
Yep.
And then your next step is now instead of that equaling 0, you're going to introduce the functional memory.
Yep.
And
So-
then when do you introduce the variable coefficient, the epsilon?
Okay. So after introducing F, I'm thinking the kind of F that I want to design is the kind of F that has discontinuities.
Okay.
Because we are finding ways, just like it was done when solving for the fixed point iteration, of translating this system that we have, the problem that we have, of translating this problem back to this form by just dividing this sum. There's some mathematics in between. Yeah, that doesn't violate the chemistry we're doing here. So after doing that, means if I design F that is discontinuous, I've accounted for this somehow, because this is what is bringing the discontinuity in the problem. And then after that, we have some epsilon that is designed already in the lab. I think I'll start with checking for that, because for starters, this epsilon, I need this flow arrays. It's okay, it's fine. It's just a charge density. It can be Gaussian. But this is what is bringing the discontinuity, moving from 8 to just 1 in the system. Yeah, so we have that. But we are just going step by step. First, assume it's 1, then introduce F. So if we introduce F, then I'll just be correcting F, not correcting the 5-point stencil. Yes, Bunja.
You refer to water solvent.
Yeah.
So I would like to know if this techniques that you apply to those of the water solvent systems or any other systems a solvent can be.
Okay, so I referred to water because everything that has been done on water. Why? Because water is really hard to model. Chemistry weight is clearly disordered, and I don't want to go to the chemistry. So, but anything that has a dielectric, for example, I gave the dielectric constant of water to be 8, but any liquid that has a dielectric, which I think they do, can be modeled because it is a liquid then. So I can design epsilon r that moves from epsilon naught is equal to 80 for outside the region, and then 1 within the region. This is for water. It can be anything. But the reason as why it's water now, because water is, you can see the dielectric constant itself is much higher. So it's disordered and hard to model. Yeah.
Yeah, thanks.